Hello friends. So let's see a question that I will discuss in RCC. First of all, let me introduce myself. My name is M.K Singh, Mithilesh Kumar Singh. I used to teach in ESE. Mainly I am teaching RCC here. I am a civil engineer and I have worked in CPWD for many years. Starting from my career from junior engineer to superintending engineer, I have spent a long years in CPWD, and I was selected for engineering services examination in 1997, and after that I was working in CPWD up to 2017 when I took voluntary retirement, and after that now I am engaged in teaching job in mainly in ESE, and I am teaching here RCC. So here I will discuss one question on in RCC, and this question will be this one. This is a beam with torsion effect. This beam is, and we will design this beam, how we can design a beam when it is subjected to torsion. I will explain the concept here, and we will discuss this question. Here you will understand how a beam when it is subjected to torsion may get affected and how it can be designed. So this becomes a important questions if you are looking for GATE or for engineering services examination. So here you will not only understand for design for torsion, you will understand even how you can design the beam for bending moment, how you can design for shear force, and then finally how we provide side face reinforcement. Everything you will understand here. So this will be a complete design of a RCC beam when the beam is subjected to different values like bending moment, shear force, and torsional moment. First let me explain you how the torsional moment are developed in a beam. See, suppose there is a beam. This beam may be simply supported, may be fixed, may be continuous, any type. Suppose I consider a fixed beam. Okay, suppose I consider a fixed beam, because only in case of fixed beam you can apply torsion. If it is simply supported, you cannot apply the torsion. So in this beam, suppose some loads are acting on this, like a UDL is acting on this, and if I draw the beam in 3D, you will understand in more better manner. Suppose this is your beam, and I put another beam over here that is in opposite direction, you can say in transverse direction to the main beam, and if I put a load on this beam, so this is one of the case when torsional moment are get developed in this main beam due to this load P acting at a eccentricity from this center line. This is the center line of the beam, so whatever is this distance, this will become E. So this beam will be subjected to a torsional moment also in this direction, and this torsional moment will become T is equal to P into E. So the beam will be twisted, you can say the beam will get twisted, and then torsional moment are get applied. Similarly, if a beam, suppose there is a beam, a cantilever beam is here. If I just show it like this, again a 3D figure I will draw. Okay, and this beam you assume that it is fixed at this end, at this portion. This beam may also be subjected to torsional moment. Suppose for example this beam also have a beam in this direction, and here you apply the load in similar manner. If you apply a load over here, okay, then also torsional moment will get developed due to this center line. This is the eccentricity. The torsional moment will get developed on this beam also. It is same as this beam. This is fixed on both ends. This is fixed at one end, and at center you are applying the moment. So this beam will get a torsional moment. Similarly, there may be some cases where torsion may get developed. Let's understand. Suppose there is a beam, a similar beam like this, or suppose there is a beam that is fixed over here, and this beam have a slab also. The slab is in this direction. Okay, this beam is having a slab, and the slab is like this, and the beam is just like this. So see, if this beam is fixed at this edge, obviously this beam will become like this. These are the support for the beam. These are the support for the beam. Here also it is fixed, and this is a slab. So if you look at the beam, I can show it just like this. So this cantilever portion of the slab, this cantilever portion will provide, suppose whatever load is acting on this beam, so it will provide torsion at each and every point of this beam. So many number of torsional moment. At each point you will get a torsional moment, because the beam, this beam in this case, I can show it here, that this beam is subjected to a cantilever slab at this location, and whatever is the load on this cantilever slab, this total load on every 1 meter length will provide a torsional moment. Suppose the CG of this is acting here. So wherever this load is acting, suppose this total load is W, this length is suppose X, and this W will become whatever is the uniformly distributed load into this X. Then if you multiply with this value, suppose this is X by 2, a total X है, then this will become X by 2. So your torsion moment here will become, torsional moment will develop in this direction. There will be a torsion that will become Wx square divided by 2. So this Wx square by 2 is actually the negative bending moment due to this cantilever that will create torsion in this beam. For this beam, this moment is a torsion wherever it is acting. You can calculate all these values. So whatever is the load acting on this cantilever, this is the UDL, this is the UDL, this is the UDL. So this UDL will create torsional moment for the main beam. For the main beam, it will create a torsion. You can consider only in this portion the total load, and whatever is the distance I can show, you can consider this X up to this point, and whatever is this distance, you can consider any other value also. So whatever moment you get due to this negative bending moment of the this cantilever, that will become a torsional moment for the beam. Negative bending moment of cantilever will become torsional moment for the beam. Torsional moment for the beam. So when the beam is subjected to torsion, then how we design it? That is actually the question. We will read that question again and we will solve it. Just I am explaining you what is the effect of torsional moment, how the torsion comes, and then suppose in a particular beam, suppose I have taken this fixed beam. This fixed beam, when you consider, this was the beam, fixed beam, and in this beam we have applied a UDL. You have applied a point load also at the center, and due to this point load itself there was a moment, torsional moment in this direction T. So how you can calculate the different values? This is load, suppose P. So the bending moment diagram you can draw. You can draw that what will be the bending moment diagram, what will be shear force diagram, and what will be torsional moment diagram. You can calculate different values. So see here, suppose your moment diagram is like this, having negative moment at ends and positive moment at center. Similarly, you can draw the shear force diagram that may be reducing like this due to UDL, and due to point load suddenly it will come down and then it will become like this, positive and negative. And similarly the torsional moment diagram, because your torsion is acting just at one point, your torsional moment diagram will become like this. In half of the beam it will be, the nature will be opposite, in another half it will be opposite. So you can design the beam for any one set of values. Like when you design a simply supported beam, generally you design for the maximum moment whatever is at center. Similarly here maximum moment may be at ends, so this may be a negative moment. Let's call it, suppose this is MU1, MU1 will be here, this will be VU1, this will be MU1, this will be VU1, this may be TU1, whatever are the moments. At any other location also you can design. Suppose here your moment is MU2, that may be a positive moment. Here your shear force may be VU2 and torsional moment may be TU2. So any one set of value you can take and you can design the beam. Suppose you design the beam, suppose whatever is the size of beam, see, suppose the size of beam is B by D, and you have to design this beam for a set of values like bending moment BMU. Obviously this is factored. If you are designing in LSM, we consider factored value, that will be generally 1.5 times of the working moment. Shear force, factored shear force, or you can write just MU, BMU. In place of BMU you can just write MU. VU will be the second value, that will be 1.5 times of the shear force actual, and TU will be the torsional moment, that will be 1.5 times of T, torsional moment, T, 1.5 times of T. And now we can design for these moments. Like if we look at our question, what are these values? Let's see the question and then we can start the design for these three values. So let's come back, see the question. Look at here, we have to design a RCC beam of size 400 by 700 mm is subjected to a bending moment of 100 kilonewton meter. You can consider this is the size of beam 400 by 700, overall depth. Bending moment is 100 kilonewton meter, shear force is 80 kilonewton and torsional moment of 140 kilonewton meter at a particular section. So we have to design for these values. So 100, 80 and 140, size of beam is 400 by 700. So see here, this B value is, let's write, B is 400 mm, overall depth of the beam is 700 mm. What will become the MU value? This will become 1.5 times of bending moment is 100. So this will become 150. Okay. Shear force is 80. So this will become 1.5 times of 80. So it will become 120 kilonewton. And torsional moment is 140. So it will become 1.5 times of 140. So this will become 210 kilonewton meter. Let's write down the units also. Kilonewton meter. This is in kilonewton and this is again in kilonewton meter. So how we can design this beam for these moments using M30 concrete and Fe415 steel? This is your question. So how we can do this? Let's understand. Effective cover is 50 mm. Effective cover is 50 mm. Effective cover is from where you provide the main bars, the center of that. See, suppose these are the main bars. So from center of this value is considered 50. So what will be effective depth of the beam? Effective depth of beam will become, total depth is 700 minus 50. So this is 650 mm. Okay. So these are the values for which you have to design this beam. And let's see how we can solve this question. What are the design steps that I will discuss with the question? You will get it. What are Indian Standard Code provisions about this? Those things I will discuss simultaneously. So we will design the beam as per IS 456 provisions. IS 456 provisions. So let's see how to do this. This much part you have understood. Let's see how we can do. So see, such beams, when you have to design for torsion, generally such beams are more critical in shear, and that's why first of all we must check these beams for shear. So let's see how we can check it for shear. So the first step here will be step number 1 will be how we can check for shear. Check for shear. So here I will explain you the concept also, and Indian Standard Code provisions also, and then I will explain you how to solve this question. Together we will do everything. So here number A, first of all, code suggests, Indian Standard Code suggests that calculate a equivalent shear force. Equivalent shear force. This will be including the effect of torsion. Shear force, this will be including the effect of torsion. Effect of torsion. Okay, so how we can do this? Let's see. For that, code give us a formula. That formula is VU equivalent. E for equivalent is equal to VU, the normal value of shear force, plus 1.6 times of TU divided by B. So this is the value suggested by code. This is as per IS 456, and we will check the nominal shear stress developed due to this shear force. So let's see how to calculate it. So first calculate the value of VU equivalent. This is equal to VU is 120 kilonewton plus 1.6 times of TU is 210 kilonewton meter. This is 210. 140 into 1.5. This is 210. So you will write 210 and see the units. This is in kilonewton. This is in kilonewton meter. So you should divide the value of B in meter. So although the B value is given 400, but here we will write 0.4 meter, so that your meter is cancelled and you will get the value in kilonewton. So it will be 120 plus 1.6 into 210 divided by 0.4. You got the value of 960 kilonewton. You can see the shear force that was hardly 120 kilonewton have increased to 960. So here huge change in shear force due to the effect of torsion. So when torsion comes, then we have to design the beam for a very high value of shear force, and this is the most important part that makes this beam more critical, and this beam may fail in shear. That's why we are checking it for shear first, and then only we will go for design for normal bending and shear reinforcement. So we can check the nominal shear stress next. Nominal shear stress formula you know as per Indian Standard Code. All these are empirical formula, you can say. This is called tau V equivalent, that is equal to VU equivalent divided by B into D. So let's calculate this value, and this value obviously should not be more than tau C max. इससे ज़्यादा नहीं होना चाहिए. तो अब आप देखो इसको कैलकुलेट करते हैं. What is the value of tau V equivalent? So tau v equivalent will be VU equivalent, that is 960 kilonewton. So multiplied by 1000 to convert it in Newton, divided by B and D. B is 400 mm just now, and into effective depth will be 650 mm. So check the value. 960 exponential 6 exponential 3 divided by 400 by 650. So see, I am getting the value 3.692 Newton per mm square. See, this value is not safe. This value is greater than tau c max. That value as per Indian Standard Code is 3.5 Newton per mm square as per IS 456 for M30 concrete. This you can see from code as per table number 20. You can look at table number 20 of IS 456. There you will find the value of tau c max 3.5, and code says that if a beam show a very high value of shear stress, then you should not design the beam. Even if you are designing a building by a STAD, in a STAD program also, if any beam show such result, then a STAD doesn't design the beam. Then a STAD will tell you to first change the size of beam, then only a STAD will provide you the steel detailing and reinforcement area of a steel, those things. If the beam is safe in shear, then only we can design. So here you can say that this beam is not safe in shear. So we have to redesign this beam. Redesign means we have to change the size of beam. Here you can say that the beam is not safe in shear. Not safe in shear. So what we can do? We can change the size of beam so that this beam becomes safe from shear point of view, and then only we can go for design. So here I can see the difference is too less. It is 3.692, this is 3.5. So even if I increase the size of beam a little bit, then also it will become safe. And see, generally in this case, when the beam is found not safe in shear due to high value of torsion, then what we do, generally we increase width, not the depth. You can increase depth also, but if I am increasing width, then you will get benefit here also, in this formula also, and in this formula also, at both location, because B is here also and here also. So at both location you will get benefit. So let's increase increase the width. Even if your tau v value becomes less than 3 also, then also you can design it more comfortably. Even it becomes near about 2 also, then also you can design it comfortably. So 3.5 doesn't means we have to design just near 3.5. You can reduce the size of beam. So that means you can increase the size of beam and reduce the value of tau c max, tau v value, so that it becomes much less than tau c max, and then we can design it. It is better if I take a round figure, 400 hai, suppose I take 450 mm or 500 mm, and then we design the beam, then it will become okay. So now I have to increase the size of beam. I will do it in next slide. So see here, let's change the size of beam. Change the size of beam. Okay. You can change it to 450 mm also. You can change it to 500 mm also. In both cases, it will be safe. If you want to keep a round figure, make it 500. If you want to keep 450, that is also okay. So let's, this is just a trial. Let's assume you will understand how much depth, how much width will be required. Suppose I increase B to, suppose I increase to 450 mm. That will also make it safe. So in this case, now again calculated, VU equivalent will become what? VU equivalent will become VU plus again 1.6 TU divided by B. Put all the values factored. 120 plus 1.6 into TU is 210 divided by, now you can write it 0.45, that is equal to 120 plus 1.6 into 210 divided by 0.45. So now it is 866.67 kilonewton. So what will be tau v equivalent now? Tau v equivalent will be VU equivalent divided by B into D. Again we can check it. The value will become 866.67 into 1000 divided by size of beam now is 450 mm by 650 mm is the depth. So how much? Into 1000 divided by 450 by 650. See, I am getting the value. It is 2.96 Newton per mm square. See, you have both option. This is also correct. This value have become less than 3.5. So it's okay. This is less than 3.5 Newton per mm square. So now your beam is safe. We can design it. Or if you want, you can reduce even further. You can reduce this value by increasing B to 500 mm. It will further get reduced. 500 पे भी आप डिजाइन कर सकते हो. So no problem. Let's design it with 450 mm. It's okay. Your beam have become safe. So unnecessarily we should not increase the size. So let's design with, this is okay now. This is okay. This is okay now. So let's design the beam with a width of 450 mm. So let's use width of the beam B is equal to 450 mm. Overall depth is 700 mm and effective depth is 650 mm. Okay, even this beam is okay, safe. Now we can design for these values, and your design values you know already. Now this beam is safe in shear. This is safe from shear point of view. So let's come to the design for moment and shear reinforcement that we will do. So first of all, let's design for moment. So how we design for moment, let's understand. Let's go to next page. Now it is safe from shear point of view. So a step 2 I will take. Let's take a step 2. We will design for moment. We will design the beam for moment. Okay. See here, your moments are, mu is one moment. This is equal to 150 kilonewton meter. I can take it. See the question. Yes, here it is 150 kilonewton meter, and torsion is 210. So mu is 150 kilonewton meter. Torsional moment is Tu is 210 kilonewton meter. So now we have to combine the effect of these two. So how to combine? So code suggests that you calculate, number 1, you calculate a equivalent moment, or you calculate a value of moment due to torsion first. Moment effect due to torsion you can calculate. First of all, this value is called MTU, we call it, ठीक है, moment due to torsion. The value as per Indian Standard Code is, the formula is TU divided by 1.7, 1 plus D divided by B. This is the formula. So let's calculate its value. So this MTU will become TU, that is 210 divided by 1.7 into 1 plus overall depth of the beam is 700 divided by a small B we have calculated 450 mm. So let's do it. 210 by 1.7 into 1 plus 700 by 450. This is equal to, see here, 315.7, 315.68 आ रहा है, 0.7, or you can take a round figure, say 316 kilonewton meter. So now see how we can design the moment. Your moment, that moment is also there, and this is the moment due to torsion. And see, this value is even greater than this one. So here code suggests that design this beam for two moments. Design this beam now for two moments. So what are these two moments? Let's understand. First moment will be number A, mu equivalent 1, first equivalent moment, including the effect of moment due to torsion plus normal bending moment. And second moment you have to design for, that is called mu equivalent 2. It has to be designed for MTU minus mu. For this remaining moment, MTU minus mu, see, this value we calculate only when MTU is greater than mu, and here MTU is greater than mu, and that's why we are calculating this value. When only when MTU is greater than mu, then you design for mu equivalent 2 also, otherwise you will design for mu equivalent 1 only. So see the values, what will be the values of these two moments. This moment will become 316 plus 150 is equal to, and this moment will become 316 minus 150. So the value will become 316 plus 150, it is 466 kilonewton meter, and this moment will become 316 minus 150, so it is 166 kilonewton meter. But both of these two, for these two moment be designed differently, be designed in different way. I will show you how to design for these two moments. You can understand. First we have calculated these two moments, and these two moments are considered in opposite direction. These two moments are, see, this moment is considered a moment same as whatever is your moment mu. This moment is considered similar moment as, same की जगह पे similar लिखो. Let's write similar moment as of mu. This is a similar as mu. Similar means if your moment mu is sagging or positive moment, then this will be also positive moment. If this is negative, then this will if mu is negative, then this will be negative. Here suppose in question it is not given, however we can suppose that, we can assume that the moment given mu is equal to 150 is, for example, suppose this is a positive moment, positive bending moment, then this 466 will also become positive bending moment, but this will be a opposite of mu. This moment is considered as opposite of mu, so we will consider it as negative moment. So whatever reinforcement you will get, suppose for this you need the reinforcement at bottom, then for this whatever reinforcement will be needed, that will provide at top. You can understand like this, कि suppose you design the beam here like this, and for example you need just a single reinforcement, and suppose this is neutral axis. So for moment mu equivalent 1, for example, suppose this is a positive moment, then this will be the tension side of that positive moment. We can show that this is the tension portion of that this moment. So you provide a reinforcement here on this side. This is the reinforcement for mu1. Then whatever reinforcement we will design for mu2, that we will provide here. This is the reinforcement designed for mu2, you will provide on the compression face of the member. Suppose this is the compression face of the member for moment mu. If I talk in terms of mu is positive. For that, this is compression, this is tension. So this reinforcement for mu equivalent 1 you will provide on tension side, but for mu equivalent 2 you will provide on compression side. Let's name these two reinforcement. Suppose this is AST1 and this is AST2 या AST, चलो 2 लिख देते हैं, कोई बात नहीं. Just now we don't know for this moment what type of beam we need. I hope it will be a singly reinforced section required. So only one reinforcement of tension you may be needed for 466, and another reinforcement we will calculate that we will provide for this, but that we will provide at the top face. Let's calculate one by one. How to understand which type of beam we need for design. Let's see. I will discuss in next slide. So first we decide these two moments, and now we design one by one. Come to next. So see 2 ka A. We are designing first of all. Let's design for first moment. Mu equivalent 1, that is equal to how much? That is equal to this moment, 466 kilonewton meter. 466 kilonewton meter. First of all, you check the value of mu limiting. That will guide you what type of beam you will need. This formula you know, it is QBD square, and Q value for M30 concrete and Fe 415 steel will be, we have a direct formula for Q value 0.138 into FCK is the formula for Fe 415 into B into D ka square. So this is equal to, calculate it, 0.138 into FCK is 30 into B is 450 and D is 650 square divided by 10 to the power 6. You will get the moment of resistance of limiting section as singly reinforced. So this is 0.138 into 30 into 450 into 650 square divided by 1 exponential 6. Say I am getting this value 787.12 kilonewton meter. Okay, this is the moment. What is your moment? The design moment is only 466. So we can say this is 466. So we can say that because as the moment mu equivalent 1, as the moment mu equivalent 1 is less than mu limiting, so we need not to design a balanced or over reinforced section. Here we need a under reinforced section. We need an under reinforced section for this moment 466, and for that you know there is a formula. This formula you can use. This is 0.5 into FCK divided by Fy into 1 minus root over 1 minus 4.6 into this BMU mu equivalent 1, B हटा दो फिर, mu equivalent 1, and divided by FCK into B into D ka square and into B into D. So let's put all these values here. So this is AST1, let's call it AST1 is equal to 0.5 into FCK is 30, Fy is 415 into under bracket 1 minus root over 1 minus 4.6 into moment is 466 into 10 to the power 6 divided by FCK is 30, B is 450 into D is 650 ka square and into 450 into 650. So we can calculate this value. You will get the area of steel for this moment. 415 into under bracket 1 minus root over 1 minus 4.6 into 466 exponential 6 divided by 30 divided by 450 by 650 ka square into 450 into 650. See the value, I am getting the value double to 19.7, or you can say double to 20, round figure double to 20 mm square. This steel we can provide on tension face of the member or bottom side, you can say. We can decide number of bars. How many number of bars? Double to 220 by pi into 4 by, suppose I use 25 mm, it is coming 4.52. If I use 28 mm, it is coming 3.6. So we can decide number in proportion. Suppose I provide 328 plus 120 or 25, then how much? 2160, provide 25. You can select any combination. Suppose I provide 425 plus 216. If I provide, then 2365 is coming, and if I change it to 12, then it is 2189. कम हो जा रहा है तो आप 216 कर दो, no problem. Suppose I provide 425. Let's provide. It will become a little bit more, no problem. 425 and plus 2 number of 16 mm dia. The total area comes 2365 mm square. It's okay, no problem, because exact finding exact combination is somehow difficult. You can calculate, but it will take time. So let's provide this 425 plus 216. It's okay. Now we will go for design of second reinforcement for mu equivalent 2. Let's see how to do that. Second का B है ये. Design for second moment. Design for mu equivalent 2. That will be equal to how much? 166. This is 466. This is 166. For 466 we have used this formula. Now for 166. See, for 166 kilonewton meter, because it is has to be provided on top, so its lever arm will become d minus dc, and area of steel of this second moment AST2, let's write. You can calculate like this: mu equivalent 2 divided by a stress in reinforcement is considered 0.87 Fy, and lever arm you can consider d minus dc. You will get this value. So this is 166 into 10 to the power 6 divided by 0.87 into Fy is 415, and into d minus dc. D is 650 and minus you can deduct 50. So this is equal to 166 exponential 6 upon 0.87 upon 415 upon 600. See, the value is coming 766 mm square. We can provide suppose 4 number of 16 mm dia. If I provide 4 16 mm, then it will be around 800 mm square. Area of steel will be 4 into pi by 4 into 16 square. It is coming 804. 4 into pi by 4 into 16 square. This is 804 mm square. It's okay. So we will provide these reinforcement in the way as I have shown you. See the beam. This is your beam. The size of beam is, this is 450 mm. This total depth is 700 mm. 50 mm cover on both sides. Four plus 2, 625. We can provide in one layer 625. Suppose I provide 1, 2, 3, 4 like this, and 216 if I provide in the same layer. We have a full total width of 450 mm, so it's a quite large width. 450 minus, even if I deduct a cover of 50 on both sides. So 100 minus हो जाएगा 350 minus 1 2 3 1 2 3 4 minus 4 into 25 minus 2 into 16 218 1 2 3 4 5 6 1 2 3 4 5 5 gap. The gap will be 43.6 mm. It's okay. So we can provide in single layer, and at top your reinforcement is just 4 number of 16 mm dia. You can provide anyhow like this, and then we will design the shear reinforcement. That suppose you need 2 legged, then you can provide like this. In this way we can provide it. So we will design it, this reinforcement stirrup, how much will be required, we will design, and then you have to provide some side face reinforcement also. Here I don't know exactly how many number, we will calculate. These are the side face reinforcement that you will design and provide. So let's understand one by one how to design it. So for reinforcement we have already designed. These reinforcement are 425 these are 4 नीचे लिख देता हूँ 425 plus 216, and these are 4 number of 16 mm dia. Okay, chalo. So up to this you have understood the design. Now let's see the design for a step 3. A step 3 will be design of shear reinforcement, that we will discuss. Design of shear reinforcement for the combined effect of shear plus torsion. For combined effect of shear plus torsion. Shear plus torsion. Both effect you will consider, and then you will design the shear reinforcement. Let's see how to do this. Step number 3. So let's go to next slide. Here you have to use different formula, whatever code I have suggested. So let's come to 3 ka A. The first formula code suggests for a spacing of shear reinforcement is equal to ASB into 0.87 into Fy into, in place of D, code suggests D1 divided by, I will tell you what is D1, divided by Vu divided by 2.5 plus Tu divided by B1. So first understand what are these B1 and D1. So B1 and D1 are for the beam, whatever reinforcement you have provided. For example, the reinforcement you have provided, end reinforcement are here, and some more reinforcement you have provided like this, and at top also you have provided some reinforcement like this, right? So what will be, and this is a stirrup. So what are the distance between the center of these main bars in this direction is called B1, and what are the distance between center of main bars in this direction, this is called D1. Okay, so let's see. The here B1 will become, we have to deduct cover, that is 50 mm from both sides. It will become B minus 2 times of effective cover. So this will become B is 450 mm minus 2 into 50, 100 mm is deducted, so 350 mm. Similarly D1 will become total depth D minus 2 times of effective cover, So this will become 700 is the total depth minus 2 times of 50. So this will become 600 mm. So now use the formula. Suppose I assume a stirrup of two-legged, and see, generally we need a large diameter reinforcement in case of torsion, because too high value of shear and torsion is there. So two-legged, suppose I assume 12 mm dia. I suppose ki diameter you will need around 12 mm dia a stirrup. We will check the spacing. You will understand why I have written 12 mm dia directly. You will need very high value. So the spacing will become, write down all the value. ASB formula is two-legged pi by 4 into diameter ka square, that is 12 ka square, into 0.87 into Fy, that is 415, into effective D1 is 600 mm, divided by VU is how much? VU is 120 kilonewton. So 120 into 1000 you can write, divided by 2.5 plus TU is 210 into 10 to the power 6 divided by B1 is 350. So let's calculate the first value of spacing for design of shear reinforcement. 2 into pi by 4 into 12 ka square into 0.87 into 415 into 600 by under bracket 120 exponential 3 upon 2.5 plus 210 exponential 6 upon 350. So let's see the value. I am getting it is 75.6. It's okay. 75.6 mm. So 75 is a good value. And you can see even if you have used 12 mm, you are getting 75 mm. This is first spacing. There is one more formula using which you have to calculate the spacing. 75 mm. If everything is okay, you can provide at 70 or 75 mm center to center. Let's see the second formula now. This is first formula. For second formula, you will need tau c value also. Let's go to next page. You will understand. 3 ka B. Let's write. There is another formula for spacing. The spacing formula, spacing of shear reinforcement SB shall be less than or equal to. Here your formula is ASB into 0.87 Fy divided by tau V equivalent, whatever you have calculated finally, minus tau C into B, just B. D is cancelled from both sides. So let's see the values. Tau V equivalent is what? Tau V equivalent is, we can check the value of tau V equivalent, what finally you have got. Yes, see here. This is 2.96 is the final value of tau V equivalent, that we can write here. 2.96 Newton per mm square. Now let's check the percentage of steel. PT percentage. How much steel you have already provided? You have provided a little larger area of steel. 2365 you have provided, although it was required 2220. So let's calculate from this 2365. This formula will be AST divided by BD into 100. This is 2365 divided by B is 450 by small d is 650 into 100. So this is equal to 2365 upon 450 by 650 into 100. This is 0.808%, 0.81%, let us say. So for 0.81%, let's see the tau c value. The tau c value I can suggest you for 0.75%. Your tau c value is, I can see it is given in the question, 0.59. And for 1%, the value is given 0.66. So let's calculate the value in between these two. You can interpolate the value of tau c. This will become more than 0.59 plus less than 0.66 minus 0.59 divided by the difference between 1% minus 0.75 and into we have to calculate 4.81 minus 0.75. This is equal to 0.59 plus 0.66 minus 0.59 divided by 0.25 into 0.81 minus 0.75. This is equal to 0.6061, 0.607, let us say 607. So let's calculate the spacing now. A spacing of again two-legged 12 mm dia. A spacing will become ASB, that is 2 into pi by 4 into 12 ka square into 0.87 into 415 divided by, this is 5, divided by tau v equivalent 2.96 minus tau c 0.607 and divided by b. B is 450. So let's see this value, how much? 2 into pi by 4 into 12 ka square into 0.87 into 415 upon under bracket 2.96 minus 0.607 and divided by 450. I am getting the value. See, this is also a very similar value to previous one, 77.13 mm. So what value we will provide? However, you can provide 75 mm, but some more checks are applied here. That also I will tell you how we can write the spacing. So one value, one formula is suggesting 75 mm, another formula is suggesting 77 mm. Both formula is giving almost similar value. Now let's see what finally you will provide. Here you can check this value with another two value. The spacing in this case 3 का C लिख रहा हूं मैं यहाँ पे. Your spacing should not be more than, first value is called x1, second value is called x1 plus y1 divided by 4, and third value is called 300 mm. In fact, these value you will get very high value. X1 is nothing but the shorter leg of stirrup. We can calculate like this. If I calculate, see here, x1 will be shorter leg of stirrup. A leg of stirrup will be a little bit more than the b1 and d1 value. It's okay. Even if you take b1 and d1, then also you will get very high value, because b1 plus you can add diameter of main plus diameter of stirrup, you will get this b1 x1 value. b1 is how much? b1 was 350 plus diameter of main we are using 25 plus diameter of stirrup you are using 12. So this is nearly 350 plus 25 plus 12, 387 mm. And even the y1 value will be according to d1 plus diameter of main plus diameter of stirrup. You can use it. d1 is 600 mm is d1. We have used d1 600 mm. Here we have calculated. See, we are calculating leg of stirrup actually here. This length of stirrup is called x1. This length of stirrup is called y1. That we are trying to calculate. So this value will become d1. We have calculated 600. So this will be 600 plus, on one side we have 25, on other side you have 16. दोनों का half आप ले लो, plus 12. This is the exact value of y1. 600 plus 12.5 plus 8 plus 12. See, this value is coming 632.5 mm. Even if you consider 632, then also it's okay. See, the value of x1, these are very high value. You are not going to change your design. x1 is 387. This value will be how much? 387 plus this value 632.5 divided by 4. And third one is 300. So all these are very high value. These are not changing your design. Divided by 4. This is coming about 254 mm. Okay, it's okay. So what value you will provide? You will provide either according to 77, or according to 75.6. So minimum value among all these is 75.6. So according to this we can write that let's provide 75 mm center. That's all. हो गया. So that you can write. चलो next लिख देता हूँ. So we will provide shear reinforcement 2-legged 12 mm dia at the rate 75 mm center to center. Because it is subjected to torsion, that's why we are getting very low value. And last check we will do a step 4. We will provide side face reinforcement. This is a very simple check. Side face reinforcement will be provided area of steel of this side face reinforcement is considered 0.1% of total cross section area. That will be 450 by total depth is 700 mm. So this is 0.1 into 450 into 700 by 100, 315 mm square. Suppose I decide 10 mm dia bars, then number of 10 mm dia bars will be 315 divided by pi by 4 into 10 ka square. Why we are providing side face? Because your depth of beam is more than 450 mm. When your depth of beam is more than 450, it is 700 mm, and beam is subjected to torsion, then we have to provide side face reinforcement, beam with torsion. If this beam is not with torsion, then you don't need side face reinforcement, because beam is with torsion, so we need side face reinforcement. So this will be equal to 315 divided by pi into 4 divided by 10 square. See, it is coming 4.01, although you can provide 4 also, but because it is coming more than 4, so let's say 6 number, provide 6 number. Or you can neglect 0.01 and you can provide 4 number, because this is not very important reinforcement. You can provide just 4, it's okay. You can neglect this 0.01, almost 4 numbers. 4 numbers you can provide. So 2 number of 10 mm dia on both sides you can provide, neglecting that 0.01, that is very small. So you can provide 2 number of 10 mm dia on both face of the beam. Okay, so finally your design is complete and you can show the reinforcement like this. चलो दोबारा बना लेते हैं. So suppose I draw the beam. This is your beam, 450 mm by 700 mm. This is B, 450 mm. Overall depth is 700 mm. We can provide reinforcement like this. Chalo, 2 more reinforcement I can show here, and then we can show reinforcement here also. 1, 2, 3 and 4. These are 4 reinforcement. Like this. Okay, चलो हाथ से ही बना दें. And then this is your stirrup. This is your stirrup. You can provide like this. These reinforcement must be touching this stirrup. So these are, you can show it 425 plus 216. Here it is 416 mm. And then side face reinforcement, we can show just 2 reinforcement here and 2 reinforcement here. These are 2 number of 10 mm dia, here also 2 number of 10 mm dia. These are side face reinforcement, 210 plus 210, 410 है actually, side face reinforcement. So this is your beam, and effective cover on both sides is 50 mm. So finally this is your design of the beam. I hope you have understood, you have enjoyed this session. For design of torsion, this much is enough. We have just calculated all the values as per provisions of Indian Standard Code. So RCC is an interesting topic where a number of topics are there that you can go through. So for today, this much is enough. That's all. Thank you.